Hello all. This is the first lecture, which is the DC generators. The outlines of this lecture is the definition of the DC machines, theory of operation, construction, armature winding, lap, and wave, the back-induced EMF. We will begin by the definition of DC machine. The DC machine is a bidirectional energy electromechanical energy conversion device. It can convert mechanical energy to electrical energy, which is a generator, and act as generator, and vice versa, where it acts as a motor. It can convert electrical power to mechanical power. If the input is mechanical power and the output is electrical power, it acts as a generator. And if the input is electrical energy and the output is mechanical energy, then it acts as motor. The theory of operation of the generator is the dynamic induced EMF, which is the right-hand rule. We have the thumb in direction of motion. This finger is the direction of flux, and this for the current or the voltage. The voltage is equal to magnetic flux density times the length of the conductor times the velocity, where we have the flux density B is perpendicular to the conductor, and we have the conductor is moving with the speed v. Then the back induced EMF or the current will be in this direction, which is equal to I. For the electromagnetic force, using the left hand rule, we have the thumb in the direction of motion and the field in the direction of motion or direction of force, and this finger in the direction of flux and this finger in the direction of the current. Here the current in this direction and the flux or the flux density in this direction, then the force will be in to the left side, and the force is equal to B times I times L. We have the elementary DC machine. The first conductor AB in the first connectivity here is moving with the speed v to the right side, and the flux is from the north to the south. Then the current will be from A to B. And for the conductor CD, the velocity is to the left side and the flux is downwards. Then the current will be from C to D. The current for the loop will be from A to B to C to D, and this is connected to a cylinder at the terminals having two halves A and B, which are insulated from each other. And we have two brushes, which one is negative, the first one or the upper one is negative, and the lower one is the positive. After 180 degree rotation, the conductor CD will be in the position of AB for the first figure, and then the current will be in the direction to the inside of the page, and the velocity will be to the right side. For the conductor AB will be having the direction of rotation to the left side, and the flux will be downwards. Then the current will be from B to A. Then the current in the conductor CD has reversed direction from the first figure to the second figure after 180 degree rotation, and the same for the conductor from A, B, the direction of the current is reversed. Such arrangement, the flux is established using two magnets. Between them, a coil is rotated around its axis. At instant figure A, the current induced voltage or the current direction or the induced voltage direction is from A to B to C to D, and after 180 degree rotation, it will set the induced voltage around the loop for the direction D, C, B, A. The voltage collected at coil terminals could be made unidirectional by using a split copper cylinder, which is shown here, and two halves electrically insulated, and two carbon brushes in contact with these two halves. The two brushes are stationary, connected in the stationary part. As we see here, these are the two brushes, and this is the commutator. Commutator which is commutating from one coil to another, changing the connection from one coil to another with the brushes. For the elementary machine, we have the commutator is two halves of a cylinder, and each half is connected to a brush, as shown here. We have two halves, A and B. The A half is connected to the negative brush, and B half is connected to the positive brush. After 180-degree rotation, the B half will be connected to the negative brush, and A half will be connected to the positive brush. Um, For the elementary machine, the back-induced EMF across the conductor AB will reverse direction every 180 degree. And for the induced EMF across the brushes, which is E12, will be always positive. This is the voltage across the brushes. Then the voltage across the brushes is always positive, and this is the function of the brushes and commutator. In this way, the induced voltage around the loop it changes direction. The carbon brushes it change contact with two halves such that the polarity of the brushes are kept unchanged. The polarity of the brushes is not changed. Only which is changing is the polarity of the cylinders or the halves of the cylinder of the commutator terminals. If we increase the number of turns, we have turn 1 having this voltage, and turn 2 having this voltage, and turn 3 having this voltage, and turn 4 having this voltage, and turn 5, and so on and so forth, then the terminal voltage across the brushes will be almost DC constant value. What are the drawbacks or the main drawbacks of the elementary DC machine? The first one is the space between the poles is large to allow the coil for completing the rotation. Also, using permanent magnets to produce the required flux is not satisfactory, since the flux density produced in this case will be very low. Will be very low flux in case of permanent magnets. To remedy these drawbacks, we have increased the coils. We have the turn connecting multiple turns to confine a coil or to produce a coil. Then we connect coils in series with each other to form the winding. The construction of an actual DC machine is the armature, which is the power producing part, and the shaft, which is the rotating part or the part we take the output power, the fan for cooling the conductors, and the bracket to enclose the fan. We have the bearing to reduce the friction between the rotor or the shaft and the stator. We have the frame, the outer frame for connecting the poles, the stator, which is a stationary part, the commutator, the brush assembly and the brushes. This is the construction of DC machine, and we will see it in more detail in the next slides. The structure of an electric machine has two major components, a stator and rotor, separated by an air gap. The stator, this part of the machine, does not move. Is not moving part. It is a stationary part. So it takes its name stator from a stationary word, and normally is the outer frame of the machine. This is the stator, the outer frame of the machine. And the rotor, the second part. This part of the machine is the free part to move. Is normally the inner part of the machine. This is the inner part of the machine, and this is the rotor, which is the part or the power producing part of the machine. The armature winding is a power producing component in the machine. The stator in detail. First, the yoke, which is the outer surface of the machine, and it provides mechanical support for these poles and act to protect the whole machine and carry the flux produced by the poles. It carries the flux produced by the poles from each pole to the other. We have the poles. The poles are permanent magnet or electromagnet. The number of poles must be an even number, and half the poles are north and the other half is south poles. And for the north and south poles must not be adjacent to each other. The magnetic frame, which is the second part from the outside, it collects the poles and carry the flux from one pole to the other. the field winding or coils used to magnetize the poles and produce the necessary flux that cut the conductors of the armature, which is the inside part of the machine. For the rotor consists of armature core, armature winding, which is part number 2, the conductors or the coils, the commutator, this is the commutator, the bearing at the two ends of the rotor, the fan for cooling the machine, brushes is a part of the stator, not part of the rotor. The rotor in detail, armature core used to collect the armature winding. This is the armature core. The armature winding placed in the slots. This is the conductors placed in the slots to produce the EMF of the machine. And for the commutator is made of hard drawn copper segments to be hard to wear, insulated from each other by sheets of mica. We have sheets of mica, which is the black lines here. One end of the armature coils is welded to one copper segment. One end of the armature coil is welded to this part of the copper segment. Brushes are made of carbon, used to collect the EMF from the commutator. It collects the EMF from the commutator and is held fixed in position of the commutator by means of the brush holder. This is the brush holder to make the brushes at a fixed position from the commutator and with good contact with the commutator to reduce the arcing. The bearing. This is used to avoid the losses resulting from the rotation of the rotor. Friction losses and heat can be reduced using the bearing. For the fan is used to protect the motor from overheating or the temperature rise during operation, as some components in the motor depend on temperature rise. As the temperature rises, the resistance of the conductors will increase and will produce a heat loss in the machine. Machine winding, we have two winding in the machine. Armature winding, which is either connected as a wave, where the number of parallel passes equals 2, or lap, where the number of parallel passes equal the number of poles. And the second winding is the field winding, which can be separately excited or self-excited. For the self-excited, it can be series, shunt, or compound. Armature winding, we have the number of turns, which is equal to the number of conductors divided by 2. Z is the total number of armature conductors, and A is the number of parallel passes. We have A equals number of poles for lap case or lap winding, and A equals 2 for the wave case, wave winding, where P is the number of poles and C is the number of coils. We have the induced EMF equals the induced EMF per conductor times the number of conductors per parallel pass. Z is the number of conductors and A is the number of parallel passes. This is the induced EMF inside the machine. Z is the total number of conductors, which is equal to the number of coils. We have number of coils times the number of turns per coil times 2, as each turn has 2 conductors. And A is the number of parallel passes. The second part of this lecture, we will continue for the induced armature voltage, the induced torque, armature reaction, classification of DC generators, separately excited DC generator, self-excited DC generator, shunt connection, series connection, and compound connection. First, we continue the induced EMF equation. EA equals E conductor average times Z over A, where Z is number of conductors equals 2 times number of coils times number of turns, where Z is the total number of conductors, T is the number of turns per coil, C is the number of coils, and the A is the number of parallel passes. The back-induced EMF per conductor average equals average average flux density times the length of the conductor times the velocity of the conductor movement. We have the average flux density equals the flux per pole divided by the area of one pole. The area of one pole equals the pole pitch times the length of the machine. The pole pitch equals the circumference of the circle divided by the number of poles. Circumference of the circle, which is 2 pi r or pi times diameter, divided by number of poles, where tau p equals pi times diameter equals divided by number of poles, and then B average equals phi times P divided by pi times the diameter times L, where tau is the length of the pole pitch along armature periphery, D is the diameter of the rotor, and R is the radius of the rotor, L is the rotor length. The relation between the linear speed and the angular speed. The linear speed equals angular speed times the radius. For the E conductor average equals B average, phi times P divided by pi times the diameter times L times the length of the machine, which is L also L times omega times R. Here L is cancelled with L. We have L is cancelled with L. Then we can substitute D with 2R, and R is also cancelled with R. Then we have phi P times omega divided by 2 pi. This is the E conductor average. To get EA, we multiply it by Z over A. Then we have phi P omega divided by 2 pi times Z over A. We collect the constants, which is PZ divided by 2 pi A, which is the motor constant, PZ divided by 2 pi A, times phi times omega. The induced conductor force equals BIL, B average times I conductor times L. B average from the previous part equals phi times B divided by pi diameter times L. We substitute it in this equation. We have L is cancelled with L. Then phi P I conductor divided by 2 pi R. To get the torque equals times force times radius. Then we multiply the force by the radius. Then R is cancelled with R. Then we have phi P I conductor divided by 2 pi. To get the total electromagnetic torque equals torque per conductor times number of conductors. And for IA equals I conductor times number of parallel passes. We substitute these into the equations. We substitute I conductor with IA divided by A, as we see here, and multiply by Z, and multiply by pi phi P divided by 2 pi. Then we have torque equals K, which is PZ divided by 2 pi A, the same constant for the back induced EMF, times IA times phi. The induced torque and induced EMF. These equations are constant for motors and generators. For EA equals K phi omega and torque equals K phi IA. These equations are valid for both motor and generator. For the power developed equals EA times IA, or torque developed times omega. We can get torque developed by dividing power developed divided by omega, EAIA divided by omega. The power developed is the torque developed is the torque necessary to be supplied by the DC generator armature, to be supplied to the DC generator armature by the prime mover, and must be equal to the armature induced torque. The torque developed equals torque mechanical. Torque mechanical is the torque driving the generator by the prime mover, and torque developed is the torque induced inside the machine. These two torques must be equal to each other. For the power developed, it is the mechanical power that is available for conversion to electrical power. It is the difference between the power supply to the shaft and the rotational losses. The power developed equals the shaft power minus the rotational losses. This is the first part for the generator lecture. See you in the second part.